Okay, so yesterday, where we left off was that if we have a system where the effective range parameters are all natural size, name A goes like 1 over lambda, R naught goes like 1 over lambda, etc., set by the scale of the potential, then we found that in the effective field theory, we found that we could have an expansion of the vertex, which is C naught plus C2 P squared plus C4 P to the fourth. Each of these coming from some local operator with, derivatives acting different ways and so on. But we'll assume that this is what the tree level vertex looks like. And then what we found was that all these C2Ns were order 4 pi over m times 1 over lambda to the 2n plus 1. Yeah. Okay, so if we do, so this makes for very easy power counting in the amplitude, because what happens then is that when you do, you can expand the amplitude in powers of P over, or K over lambda. And we know that at leading order, we just have this vertex here with a C0 in it, and this is order 1. That's because there's no momentum dependence coming from the tree graph, and C0 has no P's in it. None of the C's have any funny scaling. Then at next leading order, we could have this graph. There's a C0 here. And we have to remember that the loop diagram here in MS bar, or MS, whatever, gives us just IP times 4 pi over m, where this P is the square root of ME. So that's the loop contribution. And the vertices don't contribute anything. And so this is order P, which will be P over lambda, relative to the first one. And then at an NLO, we would have the two-loop diagram with C naught at every vertex. And this has 2 loops, and so there's an IP from that. So this is order P squared. But also at this order, we can now also include the vertex with the C2P squared at the tree level. That's also order P squared. And so you see then that there's a progression of terms that you can include order by order, and you can feel confident that when you've stopped at some order, that the next order that you've neglected is some higher order in P over lambda. And so if you're working at a scale P, which you know is 1/10 of your typical scale of the problem, then you know that you should expect an additional 10% correction if you were to include the next. And so you have an idea of what your errors are on the total answer. And this matches very nicely onto the expansion that we found for A in terms of what I'm calling data, which are the effective range parameters, which we assume have been measured. Remember, we found this to be minus 4 pi A over M times 1 minus I A T plus A R naught over 2 minus A squared, P squared plus dot, dot, dot. And if you look at that, you see that immediately you get that C naught is equal to minus 4 pi A over M, which we are saying, and this we're assuming is on the order of 1 over M lambda, 4 pi over M lambda. And then you might have worried here that there's no new coupling constant here. So you wouldn't be able to fit any new data here. But on the other hand, the contribution is non-analytic in E. It's determined entirely by the tree level piece. And so there shouldn't be any new information. There's no contact operator that could ever possibly give you an IP. So sure enough, we see it's at next to leading order. It doesn't involve any new information. It just involves the same A that we fit here. And so the first two terms are just related by unitarity. When you get to N2LO, we have more stuff that's related by unitarity to the lower stuff, but we also have something new, and sure enough, we have some new data at that level. And so that allows us to fit C2 and so on. So if somebody measures A, R0, R1, we can do our expansion and we can fit those constants. Then we can take this theory and we can look at processes like two nucleons scatter and produce a photon and go back to 2 nucleons. We could try to calculate that because we know how photons couple to these two things with some caveats, because at some level, we'll be able to write down operators where you have a vertex coming from a 4 nucleon operator. How do we know that we need this? Well, there might be some diagrams here, like, I don't know, like say you put a C2p squared here and a C0, and you put a photon here and you say, oh my God, that's divergent. I need a counterterm. And so this might require a counterterm like that. And so now there's a new coupling constant that is put into your Lagrangian at the same order that this diagram comes in. And you have to start including this coupling constant and fitting your data if you're looking at 2 nucleons goes to 2 nucleons plus photon. So this is fine. It is effective field theory the way it is often understood, namely it's very perturbative. Okay? There's a finite number of diagrams at every order. There are no funny poles that appear in your amplitude. See, this amplitude will never exhibit a pole. So you can't find a bound state in this theory. But when we look at nuclear physics, we see a deuteron. So this clearly cannot apply to nuclear physics. And that was one of the things that Weinberg had to overcome when he asked, how can we do nuclear physics for effective field theory for nuclear physics, is where in the world does the non-perturbative physics come from? And he noticed that this diagram here, when we calculated that, remember we got an M upstairs, we got an MP from that diagram. And this M is a big scale, okay? And it appears because the amount of off-shellness of these particles is typically small, and the kinetic energy is a p squared over 2m, and that's downstairs in the denominator, so that brings an m upstairs. So that enhances these diagrams. And this enhancement in diagrams is something that is well known from quantum mechanics, and it's more pronounced the lower dimension you go. And in one dimension, it has the very well-known effect that if you have a potential, no matter how shallow, you'll always have a bound state. Okay? And if you go to a higher dimension, it's no longer true. A shallow potential does not always have a bound state, but it will always have a bound state if you make the particle sufficiently heavy. So the role of the mass in making the theory non-perturbative is exactly this M that's coming from this loop. The fact that the on-shell particles can almost be on-shell. So Weinberg used that to explain why he had to sum up lots of diagrams. We're not going to follow exactly what he's doing, but it is the physics behind how interactions can be not too strong and still have bound states and not violate this idea that, that you have a derivative expansion. So let's go to the unnatural scattering length. And again, this clearly is associated with systems with states that are near threshold. Bound states are almost bound states. If you have a weakly bound state, you have a very narrow potential. It doesn't matter how narrow it is. If your bound state is extremely weakly bound, it'll have a wave function characterized by a huge length scale set by the binding energy, not by the size of the potential. So we clearly, if we start off saying, well, we know that the exact amplitude has to look like minus 1 over a plus r naught p squared plus dot 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 minus ip. At this point, we clearly don't want to assume that this is much smaller than this, because otherwise we're doomed. The radius of convergence of a p expansion is that p has to be less than 1 over a. Now, if you look at neutron-proton scattering in the 1s0 channel, 1 over a is a scale, it's about 8 MeV. Okay, so to say you can only do nuclear physics at momenta up to 8 MeV and then we don't know what's going on, that's sort of not very good, right? We want to go to higher energy than that. So a simple thing to do is to expand, assume still that these higher order coefficients are natural, which is almost always the case, but will not expand in powers of p, but in powers of minus 1 over a plus minus ip. We're not going to assume that p is small compared to 1 over a. We'll just assume that this whole thing is small compared to r naught inverse. And if you do that with just formally here, what you find is that your scattering amplitude could be written as minus 4 pi over minus 1 over a. Sorry, I put the minus sign out. 1 over a plus ip with the minus sign out there. And then I get 1 plus r naught over 2 divided by 1 over a plus ip squared, p squared, plus r naught over 2 squared over 1 over a plus this is not squared. Now it's squared p cubed, p fourth. And then the thing beyond the effective range comes in. On. Now the question is, this looks like a decent expansion in the case where 1 over a is very small. Could we find an effective field theory with a well-defined power counting rule that allows us to do something similar like this, where we understand how how all the couplings and all the loops scale, and then we say that we're going to do some sort of expansion where at lowest order we'll automatically get this, the diagrams at next order will automatically give this, and so on. Question? I don't think so. I took out this minus sign here, was put out in front. I think this is correct, but we can check it later. Sorry?
The master.
I'm sorry?
There is M.
M. 4 pi over M. Yeah. Okay, so then the idea is that we'll do a Q over lambda expansion, where now Q is not P, but Q is 1 over A. Something like that. Scales like that. I don't mean it's exactly that number. In that case, then we'd have to call the leading term A minus 1. Where A minus 1 is minus 4 pi over M times 1 over A plus IP. A0 is minus 4 pi over M 1 over A plus IP squared times R naught over 2P squared. And so P counts as order Q, 1 over A plus IP counts as order Q. Therefore, this is order 1 in the power counting. I'm sorry, order 0, P squared, 1 over A plus IP squared. So it looks like a Q squared over Q squared. Yeah. So we assume that R0, R1, et cetera, are all natural. You got the question? That is what one typically finds. You can fine tune the bound state to be very broad, which makes A large, but there's really not much you can do to make R0 or R1 deviate much from the scale of the potential. So notice that if we take our same value for C naught, minus 4. Then this set of diagrams is equal to minus C naught over 1 plus C naught M over 4 pi times IP. And this is scheme dependent. I'm using MS. If you did a momentum cutoff, we saw the IP comes along with a plus lambda, which is your linear divergence. So this is all scheme dependent, where C naught's the bare coupling. Now I stick in that value of, did I do a sign wrong here? I really want a minus sign here. This minus sign shouldn't have been here. And that's because the leading term gives you a minus C naught. So didn't be a minus sign here. And then this is equal to 4 pi over M minus 1 over A plus minus IP. And so we see this is exactly what we call A sub minus 1. Why would it be justified to include it to all orders when before we said we only did it to leading order? Well, with the new counting, C naught has an A up there, which is a 1 over Q. I mean, I shouldn't have really written this. I should have said Q like 1 over A or P. They both can count sort of as order Q. And therefore, we see then that this definition of C naught is itself order Q to the minus 1. And therefore, this diagram here is order Q to the minus 1. This diagram here has two C naughts and a bubble, and this goes like Q to the minus 1, and this goes like Q to the minus 1, and the bubble gives us an IP, which is order Q. And so this is also Q to the minus 1. And so if you want to sum up all the diagrams that are order Q to the minus 1, you have to sum this entire bubble chain, and you get the leading term here, which, because it's not perturbative in the coupling constant, it is perturbative in a Q over lambda expansion, because we're just doing the Q over lambda minus 1, can have a pole. And so you can have a deuteron. And so this new power counting scheme allows us to define a set of graphs which can do this type of expansion. So let's now go to the next order. And what you find is that if you take C2 equals C0 A R naught over 2, then if you take the diagram where you have make the C2P squared term look like that, and you allow it to be dressed by a whole bunch of C naught bubbles, which I can draw as this diagram here, where this blob here is equal to 2 nucleons plus 2 nucleons scattering once with a C naught plus 2 nucleons scattering twice with 2 C naughts and so on. Then you'll find that this sum of diagrams, which you can also do analytically, because this is just a geometric series, gives you a 0. How do I get a 0 from this? Well, C2 has an A in it, which is order Q to the minus 1. And it has a C0 in it, which is a Q to the minus 1. So C2 goes like Q to the minus 2. And therefore, C2P squared is Q to the 0, because you're multiplying C2, which is order Q to the minus 2, by P squared, which is order Q to the 2. And then every time you add a C naught, you get a Q to the minus 1, but the bubble gives you a P, which is order Q, so it costs nothing. So you can dress it with an infinite number of these bubbles, and it doesn't change the order of Q. So this thing here will give us the second term. It involves a new coupling constant, which we can fit to R0. C2 gets fit to R0. Now, this looks like a fine scheme, except for there's something troublesome about it, which is that it's true that the infinite sum here is order Q to the minus 1. But let's look at the individual terms. So each time we add, if we have L loops, and we look at these diagrams contributing to A minus 1 with just C zeros here, this goes like C naught times C naught MP to the L. We get an M and a P from every loop. And every time I add a loop, I have an extra C naught. Now, when you plug this in, what C naught is, this is 4 pi A over M times MP, which is equal to 4 pi AP. So each thing goes like 4 pi AP to the L. And the whole point of doing this was we wanted to work at P much bigger than 1 over A. And so this is some number, which is, we're taking to be bigger than 1 raised to the L power. So yeah, formally we could do the geometric series, but every loop, higher order loop, is bigger and bigger. That's not a nice thing for an effective field theory. You want not just that the sum of the diagrams is some order. You want every diagram to be of the same order so you know what you're doing. Otherwise, how do I know that this diagram that looks huge might not be part of some very small contribution when I sum them all, you know? So to make this power counting evident, we cannot have C naught times M be much greater than 1 over P. But we have to remember, C naught is not a physical thing, right? Remember here, I told you we were working in the MS scheme. What does a scheme do? It shifts the contribution from the ultraviolet part of the loop back and forth between that and the contact term. They're always coming together. So we can always choose what we do with the ultraviolet piece here. And MS scheme is doing something we don't like. It's putting too much in the loop and not enough into C0, okay? So that suggests that this problem is really just a scheme choice problem, and that we can make everything look a lot neater if we choose a different scheme. And a different scheme means that instead of saying that the loop is IP, we take it EIP plus some number, which I'll call mu. We can do a finite subtraction. We saw that already with the linear divergence. We had a lambda there. We can make it anything we want. Okay? So what we're going to do is we're going to take, we're going to define this with a mu. So let's just see, if I define this, if I choose a subtraction scheme, and notice it's real, it's not imagining like the IP term, mu, then you can go back and you can figure out what C naught has to be. We can now redo this sum, the bubble sum, where am I? This bubble sum here, and we won't get this answer anymore. We will get plus mu. So in the new scheme, over here, Now what we have is that A minus 1 is equal to minus C naught over 1 plus C naught M over 4 pi times mu plus IP. And this has to match on to what we said was A minus 1, which is negative 4 pi over M times 1 over minus 1 over A plus 1 plus 1 over A plus IP. Okay, and when you do that, you find that in this scheme, C naught is equal to 4 pi over M times 1 over minus mu plus 1 over A. And so if you set mu to 0, you get our old result, 4 pi A over M. In the new scheme, you get this, okay? Now, notice that if we set this fictitious mass scale, which does not affect physics, because we're just moving around the contribution between the diagram and so when we fix C naught with this mu, then this amplitude becomes mu independent. So it's not physical, it's just how we divide up the contribution from the loop and the contribution from the contact interaction. If we set mu on the order of P, now what we've got is that this term that we were summing that we didn't like, C naught MP to the L. And it's probably a 1 over 4 pi when you actually do the diagram here. Let me just look at that quantity there. Well, the M over 4 pi cancels that, and we get a 1 over minus mu plus 1 over A times P to the L. Okay, and so now what happens is every contribution is roughly the same size. We don't have it getting bigger and bigger. So every diagram, so that means that every diagram here is of the same size. So we can actually look at the diagram and say everything's at the same size. This gets rid of the problem of before we said that Q was both P and 1 over A. But 1 over A and P can be wildly different in size. So now what happens is if we have Q is on the order P and mu, and therefore if P is much greater than 1 over A, mu is much greater than 1 over A, this thing just becomes unimportant, and this is just an order 1 correction. So this scheme doesn't change the result that you get from summing diagrams, but it allows you to look at an individual diagram and get a feel for how big it is. So this scheme is called PDS, which is power divergence subtraction scheme. So the way it was framed originally was the reason why this mu is playing the same sort of role as the lambda when we had a momentum cutoff, but it's not as big. We're not setting it to the UV scale, we're setting it to the physical scale. But it sort of counts the fact that there was a linear divergence. So the original formulation of PDS said, well, a linear divergence in 3 dimensions is a log divergence in 2 dimensions. So if we look at our loop diagram, we'll see a 1 over d minus 2 pole, where d is the spatial dimension, or d minus 3 pole if it's a space-time dimension. And so the rule was subtract off poles in 1 lower dimension as well as in 4 dimensions. That automatically gives you this mu here. But you don't need all that construct. You're always allowed to subtract anything you want as long as it's analytic in P. So forget the philosophy behind the original formulation. Just say I'm allowed to make a finite subtraction there. Let's just do it. Now, this is sort of weird power counting, right? We're saying that these coupling constants have some scaling property, okay? So in a quantum field theory language, it's like they've got big anomalous dimensions. The naive power counting you get by looking at the Lagrangian is no longer accurate. So why is that? Why is the scaling that we did with this non-relativistic scaling inaccurate? Well, remember when we said that the scaling property of C naught, our non-relativistic scaling argument, we said that the dimension of C naught was equal to 2 minus D. But to get that, we just looked at the Lagrangian, right? When you look at a Lagrangian, remember that H bar in a quantum field theory language comes from the path integral e to the I over H bar S, and S is made out of the Lagrangian. So when you just look at a Lagrangian, you're doing classical physics. There's no H bar in it. Classical physics is pretty good when you have weak coupling. When you have strong coupling, it's out the window, okay? So we're looking at a system with strong coupling. We're doing perturbation theory and momentum, but the coupling is strong, including C naught to all orders. So this type of scaling could be completely wrong. So normally a better way of looking how things scale is to look at how a normalization group flow. Let's take this C naught that we found, and you write down the renormalization group equation that comes with it. But let's first define C naught hat, which is equal to m mu over 4 pi C naught. That's dimensionless. And now you can just take that formula for C naught, stick it in here, and compute mu d by d mu of C naught hat, and you will find that you can write it as C naught hat times 1 plus C naught hat. And so this is the beta function for C naught hat. And if you plot it, looks like that. It's got a 0 at C naught hat equals 0. That's the trivial fixed point. That says that physics is irrelevant. This is the IR flow. There is another fixed point out here, though, which is unstable. If you're slightly off it, you'll flow to the trivial one. But if you're right on it, you won't flow at all. That corresponds to C naught hat equals -1. C naught hat equals -1. Well, C naught hat is this. That means that C naught must equal -4 pi over mu. That's what happens when A is infinite. If A is infinite, this is 0. C naught is negative 4 pi over m mu. Stick that in here, you get C naught hat is -1. So we see that the infinite scattering length problem is a non-trivial fixed point. And like fixed points in condensed matter systems, it's scale invariant. Okay, you've got an infinite scattering length. There's no length scale in the problem until you start probing deeper and looking at that R naught. This is called a unitary fermion, and it can be constructed in the laboratory in atomic physics experiments because they do something with magnetic fields, they get a Feshbach resonance, and they find they can make infinite scattering length. So this is a really interesting system, a scale invariant system. There aren't that many scale invariant systems you can study in nature. And what we're saying is that nuclear physics is closer to this fixed point than that fixed point. Because the neutron scattering length is so long that in some sense, we should be near this one to start with. And when you're at a non-trivial fixed point, the scaling of operators is completely changed. Your anomalous dimensions are order 1. So in fact, what we're finding is that C naught becomes relevant or marginal. In fact, it's exactly marginal if you sit exactly here. And that's why, in that language, why we're summing up so many. Well, earlier with the non-relativistic scaling argument, we said it's an irrelevant interaction. So this is the basis for doing physics in the pionless EFT. And so you can now, if you just fit the C's to the effective range parameters, that's sort of boring. You haven't done anything you couldn't have done by just doing an effective range expansion, no additional information. But now you can use this theory to start doing other calculations. And so I'm just going to mention one which you might look at if you're interested. I dropped the reference here, but it's in my notes, but it's a paper by Gautam Rupak, who was a graduate student at the time at University of Washington, and is now a professor in Mississippi. He looked at NP to D gamma. And this is a process which is of critical importance to nucleosynthesis in the early universe. There's a competition. The neutrons, in the beginning, they're neutrons and protons, they're in thermal equilibrium, but as the universe cools, the weak interactions go out of equilibrium, the neutrons start decaying. But roughly at the same time, magically, because of the way the universe works mysteriously, at the same time, this capture cross-section starts getting important. So there's a competition between the neutrons decaying into protons versus getting captured into deuterium. If they all got captured into deuterium, there wouldn't be any hydrogen left, okay? And there would be no life. If they decayed too fast, there'd be just hydrogen and no helium, and it would be much harder to seed the early stars. So it's a very critical process, and you need to know it very near threshold, which is hard to approach experimentally. So this was a very interesting calculation that he took to fourth order, which is real brute force. And so what he did was, the types of diagrams he computed was you invent an operator that can create a deuteron. We'll call it an interpolating field. So basically, what you do is you just take two nucleons with some projector in here that gives something which is in the 3s1 channel. So it combines the spins to be spin 1 and combines the isospin to be 0 and angular momentum 0. It'll create a deuteron with some amplitude. We don't know what that amplitude is yet, in principle. And then you have to look at diagrams where an N and a P come in, emit a photon, and then create a deuteron. And you can put the photon on either leg. Or you could sum up bubbles, because the bubbles don't cost anything. And put a deuteron interpolating field in one of the bubbles and have a photon coming off one of the bubbles. You have to add up all these diagrams. There's an infinite number here, but again, it's a geometric series. You can do it. But then, of course, you need to make sure that you're dividing out by the wave function renormalization, which is a fancy way of saying dividing out by the probability that this actually creates a deuteron. So for the wave function renormalization, you have to look at the amplitude for this thing. Sum of all these diagrams to have a pole at the right place with the right residue, right? The residue is the wave function renormalization. If the residue isn't conventional, then this won't give the right answer. So you have to find the right residue there. And so with these sums of diagrams, you end up getting the lowest order calculation, except for the one thing I didn't put in is, what is this vertex? It turns out the NP-D gamma, for reasons I actually forget, involves a magnetic photon. So you cannot use the covariant derivative in the coupling for that. What you have to do is you have to put in this operator, which is the anomalous magnetic moment operator. And so you have to add LB, which is equal to E over 2m nucleon times n dagger times kappa 0 plus kappa 1 tau 3, which is the isosinglet and isotriplet anomalous magnetic moment. And these are already measured. I guess Robbie did that, and at least the proton. And so these numbers are known. And so this is what provides the coupling of the photon. And so when you've computed these diagrams, which are not very difficult diagrams, in the end, you've got the lowest order prediction for NP to D gamma. At next order, I'm sorry?
Your N is a doublet of.
Yeah, N, I'm sorry. N is neutron proton. And
Where is the flavor, the photon couples to proton? Or is it
the photon couples to either because the neutron has an anomalous magnetic moment. And the relative strength is given by the sum and difference of those two numbers. At NLO, oh, sorry, question? Yeah. With a photon coming from the vertex. Yes, I'm getting to that. But it doesn't appear at this order. And the reason why you know it doesn't appear at this order is because it's not required as a counter term. There's no divergent diagram that requires that here. Now you go to NLO, you have to start including your C2P squared diagram. So you can have diagrams like this and bubbles, or simply, you know, sorry, that's right. Then you can have things like that, and insert C0 bubbles everywhere. Your wave function renormalization now has to include this diagram. Again, the square is the C2P squared. But you find that if I draw this diagram here, this is divergent. The one with the C0 wasn't, but the C2 has an extra P squared in there, so it makes it less convergent. So therefore, this requires a counter term looks like that. The photon can couple to this two-body current. And so now you have to put in a new operator. And we're using a bit of philosophy here, which is common to most effective field theories, which is that the order where an operator appears is the order where it's required as a counter term. Now, in principle, it'd be very hard to make it smaller than that because you have these huge quantum corrections that are trying to make it big, but you could in principle have it be bigger than that. But in the strong interactions, basically, the assumption is that they'll come in at the order where they're needed, and then if you fit it to data and you find you have a huge coefficient, you were wrong, okay? So that's the idea there. And that operator then looks like this operator. It's got a coefficient which is called L1. This is a new coupling constant. And you have a N transpose times a projection operator onto with a vector index. So this is a spin 1 projection operator times daggered times an N transpose P3 and a different projection operator times a magnetic field. So this is, forget what is this? It's what? I forget what it is. I'm sorry. I see. Okay. Sorry, I don't remember the details of this calculus, but this is sort of what the operator looks like. It's got 2 N daggers, 2 N's, got some spin flavor projection operators. It's got to have a vector index to dot in with the B, get the photon in there, and then it has an unknown coefficient. You're going to have to fit the data. So when Gautam was finished, it's in the PDF notes that should be available to you. There's a plot there that he gave where he shows the data points, which get pretty sparse as you get close to the threshold. And his dotted curve is this theoretical value that he gets from the effective field theory, and it fits bang on all of the data, and now gives theorists who want to understand what's going on in Big Bang nucleosynthesis something to work on with the at values where there is no data. And so that's the value added of doing an effective field theory for something like this, which is that a finite number of constants can give you a lot of different predictions. Any questions? There's a big literature on calculations done for Compton scattering, electromagnetic form factors, all sorts of things. And if you ever want to see how these types of calculations are done, there you can find out. I recommend that if there a new effective field theory is developed, jump in at the beginning, because then you can publish papers on lowest order calculations. If you wait too long, you have to do N4LO, and it's a lot of work. So I'm not going to be talking about EFT for nuclear physics beyond this, at least not directly. Yeah.
Right. If I do HQET for
I'm sorry, why is what?
proton, the zeroth component, right? Not just the sigma dotted with B, but
I'm sorry, what?
If I do an HQET of a fermion with electromagnetic something, the first term appears the zeroth derivative or dt term, corresponding there is an A0 term. We don't include.
You mean from the covariant derivative?
Yeah, for photon.
Yeah, no, I agree. There are those are called electric photons, and I forget why, but they're not relevant for this. Do you remember?
Okay. Yeah. Got this.
And in fact,
It has to do with conserving spin and angular momentum
Right,
and all that.
So that's the, yeah.
but if I, okay, if I pick the prime interest, I'm going to talk briefly about one, say capture or turn it around breakup. And so it's doing one breakup, then
Yeah, so then you'd use the photon coupling from the covariant derivatives. So I want to go back to quantum mechanics for a few minutes. Remember, we said that if we do the non-relativistic scaling, we get the scale is like 2 minus d, where d is the space dimension. And so you might think something interesting happens at d equals 2. Because then the classical theory is scale invariant. The scaling dimension of C0 is 0, so it behaves like a gauge coupling in 4 dimensions. And what happens then is that, I showed over here that quantum corrections can completely change the scaling behavior if you have strong coupling in 3 dimensions. But here we have but whenever you have a coupling where the classical scaling dimension is 0, we call this, Wilson's language is this is a marginal operator. Remember, negative dimension was irrelevant, positive dimension is relevant, and 0 is marginal. Then the classical system says it's scale invariant, and now a quantum correction, no matter how small, will tip it typically one way or the other, towards relevant or towards irrelevant. And it doesn't have to tip it much to have a completely dramatic effect on the low energy physics. And so this is where asymptotic freedom comes from. And you can see that in this quantum system in 2 dimensions from a delta function potential. So I thought I would show you that. And that's interesting because it generates exponentially large mass hierarchies. So let's do square well again. In d equals 2. Now what you find is that your inner wave function looks like an ordinary Bessel function of kappa r. And my notation is the same as it was before for kappa and the depth of the square well. And psi greater then has this outgoing wave, which looks like very similar to what we had in 3 dimensions, only now we have ordinary Bessel functions instead of spherical ones. And instead of an n0, we call it y0. Oh, sorry, kr. So, and now you do your matching at the boundary. Where delta is the width of your square well. And you find that the interesting quantity in 2 dimensions is not k cotangent delta, but cotangent delta, one lower dimension. Is k j0 of delta kappa y1 of delta k minus kappa j1 of delta kappa y0 of delta k divided by k j0 of delta kappa j1 of delta k minus kappa j1 of delta kappa times j0 of k delta. Now, you can expand this in k. And what you get is that this is equal to twice of J0 of alpha. Remember that the potential well make sure I did that right. Yeah. I guess no 2. Sorry. I actually don't remember the power of delta in here. I won't write it down. I think it's that. And then kappa is square root of k squared plus alpha squared over delta squared. So now you expand it, and what you get is you get J0 of alpha over alpha J1 of alpha plus a log of delta K over 2 plus the Euler constant divided by pi plus order K squared. So this looks radically different than what we found in 3 dimensions where the first term is a constant. Okay, it's got this log K in there. And that is going to be have a huge effect. In particular, we find that cotangent delta goes to minus infinity as K goes to 0. And so the phase shift must vanish somewhere below K. And cotangent delta must change sign. And if you ask, where does it change sign? You find that K star is approximately equal to twice e to the minus J0 of alpha over alpha J1 of alpha minus the Euler constant, all up in the exponent over delta. So this tells you that this fancy point where something interesting happens is exponentially related to the natural scale 1 over delta. And whether this exponential factor is big or not depends on alpha. But it's exponentially sensitive to it. For weak coupling, alpha much less than 1, you find that that this quantity here looks like 2 over alpha squared. So e to the minus the Euler constant, just some factor. So you find that this is proportional to e to the minus 2 over alpha squared 1 over delta for weak coupling. So that tells you something interesting happens at an exponentially smaller scale than the natural scale. It's exponentially smaller mass scale, exponentially longer distance scale. And we'll call this scale, K, instead of calling it K star, I'll call it lambda, okay? And it'll be the analog of lambda QCD. Yeah. It's an infrared scale, sorry. It's a low scale, like lambda QCD is a low scale where you set the strong coupling constant at the Planck scale, and lo and behold, there's lambda QCD down at 200 MeV. Another place where this occurs, and if I have time, I'll show you how it occurs, is in BCS theory, where your interatomic spacing is, angstroms, and no, it's Bohr radii, and the Cooper pairs are maybe 1,000 times bigger. And you might think, how in the world, with all the stuff happening in the crystal, all the vibrations and the dirt and so on, you form pairs that are 1,000 times bigger than the fundamental scale? And the answer is going to be the same, as there's asymptotic freedom in that theory. So this is easier to analyze, and more, at least more conventional, if I go to the delta function theory, which, just as before, for long wavelengths, completely replicates the low energy behavior. So I'll look at the Schrodinger equation, 1 over minus 1 over 2m delta squared plus g over m delta 2 of x, and g can have either sign. I'll look at both. Psi equals E psi. And this theory is scale invariant because if I change x by a scale, this picks up if x goes to Sx, then this goes to 1 over, then delta of Sx is 1 over s squared delta of x, and del d by d Sx squared is 1 over s squared del squared. And so both of these terms scale the same way. And so if I find a solution, it looks like I just have to rescale the size of the solution. I have a new solution with a rescaled energy. That's really weird, right? There's no discrete spectrum then. But that's not going to happen. The reason why it's not going to happen is because this is ill-defined, okay? It requires renormalization. When you renormalize, you introduce a scale. It breaks the scale invariance. That's the typical thing that happens with scale invariant classical theories. There are special ones which will stay scale invariant, free theories, for example, and conformal theories can stay scale invariant, which are strong coupling, but typically quantum mechanics breaks scale invariance. So am I supposed to stop at this point? Okay, so we'll compute the beta function for G after the break. Any questions? Yeah. It's what? Yeah.
Okay. Delta 2 x will be scaled like 1 by x squared.
Yeah, the energy will scale like s squared.
But the potential there was like alpha squared by m delta. Their delta is like 1 by r.
Oh, the point is that to make these two terms scale the same way, I don't have to rescale G. And that's the statement that this coupling constant has scaling dimension 0. So the G does not break the scale invariance. See, in 3 dimensions, the 4 Fermion operator is only scale invariant if I also scale C naught. And that is a way of measuring whether it's relevant or not. Here, G doesn't have to scale. It's scale invariant without changing G. And therefore, its dimension is 0 under the scaling. So couplings that don't scale, if all your couplings don't scale, that means your Lagrangian scale invariant. If some of your couplings scale, like you have a mass term or a 4 Fermion interaction, that means you've broken the scale invariance because you have to make the couplings scale themselves if you want to make the theory scale invariant.
But in the 2 scenarios, like when you were writing the full potential, like minus alpha squared by m delta, that scale, like the full potential scaling and the effectively when you were writing in terms of delta function, that should be the same or?
I'm sorry, I didn't catch that.
So
Speak a little louder.
there it was like alpha squared by m delta, right? So it was like 1 over m and 1 by r. Here it's just 1 over m and 1 by r square. Are the two things same? Or?
I'm not following. Sorry.
He's asking here, this m is similar to that m, but the potential here scales as 1 over r.
Yeah, so I'm not completely sure about this delta. I didn't have it in my notes. Okay, okay. This G. Okay, in the non-relativistic scaling, this m doesn't scale, okay? So it doesn't matter that I put the m in there. This G will match on to, this G over m will match on to C naught in the field theory.
So G here is dimensionless.
I put in the M here because then it makes, since this has the same
Yeah.
length dimension as that,
Yeah.
then G is dimensionless. Okay.
Any other questions? David, I had one quick question. You get this exponential scale, lambda IR. The lambda IR,
The what?
the lambda IR, this scale.
Oh, yeah.
So like lambda QCD, is it also RG invariant? Can one show that? Is this, can I show that this is RG
lambda
invariant?
QCD. It's where the coupling blows up in the infrared.
No, no, but is this RG invariant, renormation group invariant number?
Yes,
Like lambda QCD?
yes. It's defined as the point where the phase shift changes sign, which is a physical measurable quantity.
Okay, so we'll take a break. Come back at